You might be listening to this on a machine that, frankly, would look like a literal alien spacecraft to someone back in 1994.
Oh, absolutely. It would look like government lab tech.
Right. I mean,
Sure.
seriously, think about the device you're holding right now or, the laptop sitting on your desk. It has dozens of processing cores.
Yeah.
It has gigabytes upon gigabytes of RAM.
Just an absurd amount of power.
Yeah, exactly. So why does it take longer to open, like a simple chat app today, than it took a dusty 486 PC to boot up an entire operating system in 1995?
It is the great paradox of modern computing, honestly.
It really is. And today, we are exploring the hidden, sort of sedimentary rock of modern code. We are pulling insights from a really fascinating video essay by a retired Microsoft engineer. It's on the YouTube channel Dave's Garage.
Yeah, it's a brilliant breakdown.
It is. We're diving into how business incentives basically ruined loading times and the surprising role AI is playing in making it all a whole lot worse.
So, okay, let's unpack this, because to me it feels like we bought this massive, sprawling mansion, but somehow we're still, like, bumping our elbows in the hallway every single time we try to walk to the kitchen.
That is a great way to put it.
Thanks. I mean, is this just because modern programmers are lazy? Or do they just get worse at their jobs?
Well, it's a very comforting myth, right?
Yeah.
Especially for, like, veteran developers to just blame it on a lack of talent or effort today. But the reality is that today's developers are dealing with a level of massive layered complexity that 90s programmers just didn't have to navigate.
Right, the landscape is totally different.
Exactly. I mean, they have to juggle these nasty threat models, intense security risks, concurrency across all those multiple processing cores we mentioned. Plus, internationalization, accessibility requirements, and just heavy, heavy privacy and compliance baggage. Yeah, that makes sense. The environment is objectively more complicated to build in. The demands on the software are way higher.
Yeah, but, and this is the crucial part, back in the 90s, hardware wasn't a given. It was more like an ocean that was actively trying to drown you every single day.
Wow, an ocean trying to drown you.
Yeah, because memory had a strict budget. Startup time had a budget. CPU usage had a budget. If your feature blew that budget, you didn't just ship it anyway and hope the user's computer could handle it.
You couldn't. The computer would just freeze.
Right. You stayed late night after night, making the code smaller and faster until it behaved. There was absolutely no casual assumption that the hardware would just, float all the boats.
Having less really forces you to be clever, I guess. Like, take Bill Gates and Paul Allen fitting a fully featured basic interpreter into just 8 kilobytes of memory.
Oh, yeah, a classic example.
Right. Not megabytes, not gigabytes, just 8K.
Yeah.
And they didn't do that to show off. They do it because they physically didn't have 12K.
Exactly. And if we connect this to the bigger picture, living with that kind of extreme scarcity, it created an incredibly intimate relationship between the code and the hardware. Developers understood the actual physical mass of what they were building, like they knew intimately what a page fault was.
Wait, let's pause on that because the mechanics of a page fault are actually fascinating.
Yeah, go ahead.
So when a computer runs out of its super fast RAM, it has to go fetch data from the much slower hard drive, right? And in the 90s, you didn't just see a cute little loading spinner when that happened.
No, not at all.
You physically felt the machine stutter. Like you could literally hear the disk drive grinding.
Yes, the heavy clicking sounds. Which actually brings us to the Windows 95 taskbar clock. If you recall, that classic digital clock down in the corner, it only showed hours and minutes. It didn't tick down the seconds.
I always assumed that was just an aesthetic design choice, like just to keep the screen uncluttered.
Most people did, but they actually measured it during development. They realized that painting those individual seconds on the screen, every single tick would constantly wake up that part of the system.
Oh, wow. Just for one number changing?
Yes, and that action would trigger a memory page fault, bogging down the entire operating system's RAM budget just to show time passing.
That is wild.
Yeah.
So they just cut the seconds entirely.
Exactly. Every single byte was sacred back then. It was a discipline imposed by the physical limits of the machine.
I mean, I get the beauty of that discipline, but I have to play devil's advocate here. Aren't modern tools and, abstractions supposed to be a good thing? I don't want engineers hand-coding everything by candlelight just to save a few kilobytes.
Well, it's funny you say that because writing the original Windows Task Manager in raw Win32 by candlelight was pretty much exactly what they did back then.
Oh, seriously?
Yeah, Win32 is essentially the native language of the Windows operating system. When you code in raw Win32, you are talking directly to the metal. There are no safety nets, no helpful frameworks doing the heavy lifting for you.
So you have to spell out every single step.
Every step. You have to manually tell the system exactly how to draw a window, how to allocate memory, and crucially, how to free it up. It is painstaking, grueling work.
Right, so abstractions are how civilization advances, basically. A good abstraction hides all that painstaking work. It lets a team of 3 people build an app today that used to require an army of 50.
True. But those abstractions come at a price. It's a concept the original essay calls abstraction without cost accounting.
Abstraction without cost accounting. Okay, what does that mean in practice?
It means abstractions are never actually free. They just hide the complexity from the programmer and the cost of that hidden complexity. It gets transferred directly onto the user's CPU, their battery, and their memory.
Okay, let's break down how that actually taxes the hardware. Because when I click an icon to open a modern, supposedly simple utility app, the computer isn't just executing a direct command anymore, is it?
Not at all. Behind the scenes, that one single click sets off an absolute avalanche. First, the app might spin up an auto-updater.
Okay, checking for new versions.
Right. Then it launches a telemetry pipeline to track how you use the app, which, by the way, requires buffering data in your RAM and holding open background network connections.
Just to spy on my clicks, basically.
Pretty much. Then, rather than drawing a fast native interface, it boots up a full web rendering engine.
Wait, basically opening a hidden invisible web browser just to run a desktop app.
Yes. Running a JavaScript engine inside a security sandbox layered over a GPU compositor, utilizing a user interface framework that itself depends on like 6 other frameworks.
Oh my God. And also, so the developer could easily drop in a fancy drop-down menu without having to write it from scratch.
Exactly. The
Okay.
computer's processor has to translate your single click through all of those layers, web engine, JavaScript interpreter, sandbox, just to draw a button on your screen.
So this massive pileup is what we can call a performance sedimentary rock.
That's a perfect term for it. It's layers and layers of compressed digital sediment, just added over years by totally different teams.
Which perfectly explains why a basic text editor or a chat app suddenly demands 800 megabytes of RAM. And that sedimentary rock isn't just code the original developer wrote right. They are also importing massive libraries from other people just to get one tiny feature.
Oh, the dependency explosion. Yes. You want a date picker. Download a third-party dependency. Need a chart control. Download another one. Before the app even launches, the developer has imported a minor empire of other people's code.
It feels like third-party code is treated like an all-you-can-eat buffet now. The problem is, you aren't just getting the date picker. You are inheriting its startup costs, its memory usage, its security vulnerabilities, and its own nested tree of dependencies.
Yeah, it's like inviting someone over for dinner and they bring their extended family, their pets, and their neighbor's marching band.
That is exactly what it feels like. In the old days, a dependency was viewed as a massive liability until proven absolutely necessary.
Right, but now the default is just pull it in first and worry about the consequences later. They just assume the user's hardware will magically eat the bill.
But this massive shift in how code is built raises a huge question for me. If these dependencies cause so much bloat and users genuinely hate slow apps, why don't tech companies prioritize fixing them?
That's the logical question.
Right. From a purely capitalist perspective, making a product that frustrates the person using it seems like a terrible business strategy.
Well, what's fascinating here is how the business incentives themselves have completely inverted, and it tracks back directly to how software is sold.
Oh, you mean the shift from boxed commercial software to subscriptions?
Precisely. In the 90s, you went to a store and bought a word processor once. The experience was the product. If it felt laggy or chewed up your system memory, you noticed immediately.
And you told your friends not to buy it.
Exactly. But today, software is rarely sold in boxes. It's sold on recurring monthly subscriptions. And internally at these companies, it's judged by monthly active users, daily engagement metrics, and feature velocity.
Feature velocity,
Mm-hmm.
meaning how fast a team can push out shiny new updates to justify the subscription cost.
You got it. That changes the math entirely. The corporate machinery is optimizing for metrics that just don't capture the user's frustration with a slow loading screen.
So think about it from the inside of the company. If a developer builds a flashy new feature that increases cross-selling opportunities, they get a promotion. They get a standing ovation.
Absolutely. And if that same developer spends 3 months refactoring code to cut the app's startup time in half,
They probably just get a polite nod in a retrospective meeting.
if they're lucky. Unless the app is so incredibly slow that users are canceling their subscriptions en masse, deep performance work simply isn't rewarded.
That is so frustrating.
And furthermore, modern development is structurally fragmented. It is incredibly siloed. One team builds the outer shell of the app, another team owns the back-end database, another handles telemetry, and someone else builds the user
Oh,
interface.
I see where this is going.
Yeah.
Because of those silos, no single person is actually in charge of the time the user spends staring at the screen waiting for the app to load.
Exactly. Nobody owns the end-to-end responsiveness. The user experiences the app as, big and heavy, and that's a devastating critique. But big and heavy doesn't map neatly to any one team's task tracker.
Yeah.
So the bloat just gets ignored for years.
The industry standard basically quietly slid from true excellence-like, building something fast and elegant, to what is essentially an apology with a budget.
Mm.
We've settled for, well, it doesn't suck on the laptop once it's warmed up.
Yeah, just give it a minute. The laptop fans will quiet down eventually.
That's not a standard. That's a surrender. We've lost this essential systems literacy, the ability to know exactly where the processing time is going and how a whole system interacts. And that loss is colliding with a massive new trend.
Oh boy, here we go.
Yeah, here's where it gets really interesting. Everyone is talking about artificial intelligence making coders 10 times faster. On the surface, that sounds like a massive win. If AI speeds up development, shouldn't developers finally have the time to go back and fix all these performance issues?
I have to pour some very cold water on that idea.
Go ahead, crush my dreams.
AI is absolutely a useful tool. Let's be clear about that. It's great at writing boilerplate code, generating tests, getting developers unstuck. It writes at industrial speeds. But AI generates what we can call median code.
Median code, so average code based on its training data.
Yes. And average code, historically speaking, is not lean, ruthless, performance-conscious code. Median code is inherently verbose. It's bloated, overly defensive, and relies heavily on those thick, sedimentary layers of abstraction we just talked about.
Right, because it learned from all the bloated code on GitHub.
Exactly. AI has absolutely no native instinct for performance.
It doesn't know what it feels like to run out of RAM or wait for a page fault. It doesn't hear the hard drive clicking.
Right. In engineering, there's a concept called the hot path. This is the critical, tightly looped sequence of code that runs constantly and needs to be blindingly fast. AI doesn't intuitively feel the hot path.
Okay, there's a highly illustrative anecdote from the source about an old arcade game called Robotron. An engineer was building a user interface and asked an AI to write a video preview for this running game.
Yes, I love this example.
To ensure it ran smoothly, the engineer set up a nice, incredibly efficient socket interface for the AI to use, like the perfect highway for the data.
And the AI wrote the code, and the video preview technically worked, but it was weirdly sluggish.
Yeah, and when the engineer investigated what the AI did behind the scenes, it was horrifying. The AI was secretly taking the raw video data, converting it into base64 encoded JSON text, and shoveling that text across the socket.
Let's explain why that is so devastating to performance. Raw binary video data is dense and efficient. When you convert binary data into base64 text, you inflate its physical size by over 30%.
Plus, you are forcing the computer's processor to do heavy encoding on one side just to immediately do heavy text decoding on the other side.
It is the most inefficient, roundabout way possible to send video bits.
It's like translating a high-definition movie into a massive text document, mailing it across the country, and having someone read it out loud to recreate the video frame by frame.
That's spot on. It passes the functional test, right? The video plays, but it abuses the hardware. And here is the real danger. The threat isn't that AI will write one obviously terrible routine that a human catches.
Right.
The threat is that AI will quietly generate thousands of slightly bloated, slightly over-abstracted, battery-greedy chunks of code.
And because it technically works, the developer just approves it and merges it in.
Mm-hmm.
I mean, a human developer producing mediocre code only works at human speed. An AI producing mediocre code works at industrial speed.
Industrial scale mediocrity. It silently adds up to a product that checks every single feature box, but is mysteriously impossible to speed up. It is literally throwing AI gasoline on the bloat fire.
So we have a situation where the constraints are gone, the business incentives reward feature output over efficiency, and we have a new tool scaling that inefficiency exponentially.
It's a perfect storm.
So what does this all mean for us? We've diagnosed the underlying disease and the new accelerant. How do we actually cure this without going back to hand-coding operating systems by candlelight?
Well, we have to stop pretending that correctness is the whole game. Just because the code passes a functional test and doesn't crash doesn't mean it's ready to ship.
Okay, so what's the metric then?
Performance has to become a first-class build artifact.
I imagine that requires instituting explicit, unbending budgets. Not vague aspirations like, let's try to make the app a little faster next quarter, but hard numerical limits.
Precisely. A team might establish a rule. This new feature may add no more than 15 milliseconds to the cold start time, or this application may consume no more than 50 megabytes of memory while sitting idle in the background.
And if they break that rule, let's say an update regresses the startup time by 18%, or idle memory grows by 300 megabytes for no user visible reason.
Then the automated system literally fails the build. It rejects the code entirely, just like it would if the program crashed.
Wow, so you treat slowness as a fatal error?
Yes, but it requires a huge cultural shift. Whenever a developer wants to add a new third-party dependency, they must answer an uncomfortable question out loud. What does this buy the user, and what does it cost the user's machine?
Not what does it cost our production timeline, but what does it cost the person using it? Because if a team adds a massive library just to save themselves 2 days of coding, they are quite literally spending the user's RAM and laptop battery to save their own schedule.
Exactly. Sometimes that trade is worth it, but teams need to be mathematically honest about it. We have normalized a lot of nonsense in the software industry.
We really have. Think about it. We accept note-taking apps that require an internet account just to type plain text. We accept utilities that install background services running 204/7 just in case we ever want to use a cloud sync feature.
Oh, the background services drive me crazy.
Right. We let minimized apps just casually burn our CPU. We have to stop treating software bloat as an unavoidable law of physics. It's not. It's a market outcome.
We get what we are willing to put up with.
Exactly. So as consumers and enterprise buyers, we have to start demanding strict performance and footprint metrics. Tech reviewers need to hammer companies on memory and battery impact just as hard as they praise shiny new UI updates. Because the second poor performance hurts sales, it instantly becomes a corporate strategy to fix it.
That's the absolute truth. And the optimistic takeaway here is that none of this is an unsolvable mystery. We know how to build great software. We knew how to do it when we only had 8 megabytes of RAM and spinning hard drives. We certainly know how to do it now with hardware that is practically magical.
We just have to bring back the respect for the hardware, keep the memory safety, keep the cloud backups, keep the accessibility, all the amazing modern advancements, but bring back the discipline.
Yes, the discipline.
The idea that idle CPU usage is highly suspicious and that latency isn't just a quirk, it's a bug. The constraints of the 90s produced good judgment because it was imposed by the physical reality of the hardware. Today, we just have to voluntarily impose that taste on ourselves.
Well said.
So, to quickly recap our journey today, we started with the incredible abundance of modern hardware. We saw how endless abstraction and shifting business incentives traded elegance for heavy, bloated software.
We looked at how AI threatens to multiply that bloat at an industrial scale.
Yeah, but by returning to the discipline of the past imposing strict budgets and actually caring about the end user's machine, we can reclaim our computers.
You know, this raises one final, really important implication that extends far beyond the annoyance of a slow loading screen.
Oh, where does it lead?
Well, think about the sheer scale of this problem. There are billions of computers, laptops, and smartphones worldwide.
Billions, yeah.
If the vast majority of them are constantly running bloated apps, casually burning hardware cycles for warmth, draining batteries, and spinning up processors just to decode inefficient media code, the global environmental impact must be staggering.
Wow. I hadn't even thought of that.
Yeah, fixing software bloat isn't just about saving your time or your battery life. Optimizing code and reclaiming efficiency might actually be one of the most massive, overlooked ways to reduce global energy consumption and fight climate change.
That is definitely something to chew on the next time a supposedly simple app takes 10 seconds just to let you type in a text box.
Thank you so much for joining me on this deep dive. Hopefully your device didn't overheat while playing it. We'll catch you next time as we continue to explore the hidden architectures of the world around us. Stay curious.